All right. So it continues to expand, and it will continue to grow as we move on. All right. And this section will define two widely used protocols and standards. The first will define the protocol, which is synonymous with role or rule. Then we discuss standards. So there's standards and there's protocols. All right. So what is the difference between a protocol and a standard? The standards are developed through the cooperation of standards creation committees. So there is committees work together to come up with the standards. And the reason for the standards to make life goes easy. So when you try to bring a product to the market, you don't have to bring a product that's completely different. So you follow the standards. If you need, for example, to open a tires company, right, to manufacture tires, all right. If you go and you build tires in different sizes, it will not fit in any car. So you have to understand what are the standards for tires, right? Then you start producing tires. If you're trying to produce parts for refrigerators, so you have to understand what are the standards for the components of the refrigerator, so you will be able part of the community. Same thing with the network. Okay, the first thing has to happen first to come up with the standards, and then everybody develop from their side whatever they need to develop, right? So that's what it is. Okay, so it's like making like a standard creation, and that will include forums and government regulation agencies, right? Um, so you have the standard creation committee, forums, and regulatory agencies, governmental agencies. Um, Internet standards is a thoroughly tested specification that is useful um, and adhere to the standard by the internet. All right. There is multi levels and there is requirement levels. So if you take a look in here, you're gonna come after a while for maturity levels of RFC. Okay, RFC request for a standard. So it starts with the internet draft, then a proposed standard. 6 months after and 2 tries, you're gonna go to the draft standard. 4 months and 2 tries, you're gonna come to the internet standard. Okay, and this process will continue multiple standards. So it could be experimental, it could be informational, and it could end up to be internet standard. So there's many standards, they are only informational. There's many standards are experimental, and of course there is internet standards, the one we see them in the colors. All right, so the requirement levels, it could be for the standards could be required, it could be only recommended, it could be elective, limited use, and not recommended. So there is different levels. If you would like to check the page of RFC, just go www here, www.rfc, and you'll see tens of the standards used in so if you paste this in here, so you could browse the RFC index using HTML ascending, and as you see in here, all the standards, it has a number and the title and some information. Okay, so there is a lot of standards. I'm sure that you also be able to search for them. There's a search. You could search all the standards. Okay. All right. So this is for your information. You don't have to do anything about it, right? Then we come to the Internet administration. Who administers the Internet worldwide? who is managing the internet. So the internet, with its roots primarily in the search domain, has evolved and gained a broader use based on the significant commercial activities. It evolved, it changed over the years, and we have the current standard right now. The main players for internet are these agencies or these groups: Internet Society, which is ISOC, Internet Architecture Board, IAP, and Internet Research Task Force, IRTF, and Internet Assigned Number Authority, IANA, and this is a very important one. Okay, very important one. Internet Corporation for Names and Numbers, ICANN, and Network Information Center, NIC. All of these are, again, just this is for your information, not necessarily to memorize them or know them, just to know the players. And this will show you how they are interconnected together. All right. Anyways, so that's the background, how to start it. Then in here, let's take a look at the OSI model, okay, and the TCP/IP protocol. So OSI model is a theoretical model. It has 7 layers. TCP/IP is a real protocol that is used in internet and has 4 or 5 layers, as we'll see. All right. So how it will work? Let's take a look in here. Forget about all of this. In here, usually when you have a communication, it has to go through steps. So it starts, for example, in real life, you have Maria. Okay, it tries to send a message. All right. Then it will have a secret code. It will have a translator, and then we're gonna go to the post officer. The post officer will put it in the mail. It will go over by a truck to somewhere. Then another post office will receive it. It will be translated, then Anne will receive it. So this is real life scenario, but that's exactly what we have it in the internet. So we start with the International Standard Organization. ISO has created the OSI. So ISO, it created the OSI, the Open Systems Interconnection. All right, so let's take a look at the OSI. So it has 7 layers. 7 layers. All right. Okay, from bottom to up, we start from the physical layer. All right. Okay, let's just start from layer 7. Layer 7 is your application. So let's say that you are sending an email. So that's your application. Or you're trying to access the www. That's your application. The client is your application. Then after that, this communication from your application, it will be presented in a certain format. It will create a session. Then it will go to the transport layer. The transport layer, we have the TCP protocol or the UDP protocol. We'll cover all of that, you don't have to worry. And then it goes to the network layer. The network layer, there is multiple protocols. There is IP version 4 and IP version 6. All right, currently mostly we are using IP version 4. The example that we have given in the drawing, they are version 4. Then you're gonna go to the data link layer, and the data link layer understands the MAC address. All right, and then you're gonna go to the physical address. So technically, that's what will happen. All right. So you will have device A and device B. All right, and they are interconnected. So you have intermediate nodes, switches, routers, and between them doesn't make any difference, right? So let's say that device A would like to send the data to device B. All right. So how it goes? So let's say that this person tries to send an email. So the first step, it's gonna go to Outlook Express, for example, to create the email. That's the application layer. All right. The application layer will create a packet, and it will package the message, and will send it to the presentation. All right. And the presentation will send it to the session. The session will send it to the transport, and of course there's more data will be added. As we go down, the data will become bigger and bigger. All right. So more data is added. So presentation, session, then it goes to the transport, to the network, to the data link, to the physical layer. Okay. Now this device A is not directly connected with device B. It has to go through a router, right? The router has only three layers: physical, data link, network. So the data will go all the way to the physical, to the data link, to the network layer. From the IP address, it will look up the destination. It will know which destination it has to go to. So it will be sent back to down a network link physical. And again, it will go to the physical, to the data link layer, to the network. The network layer will know what is the destination. Remember that the router has two interfaces, right? The PC will have one network interface. This PC will have one network interface. However, the router will have two network interfaces because it is connected to networks, right? So again, okay, the data will go from the first interface up, up, then it goes to the second interface, down, down, down. Then it's gonna go to the destination. So it's gonna go physical, data link, network, transport, session, presentation, and then application. All right. So basically, the physical path of the data from device A gonna go to the router one, up down, router 2 up down, and then it will go to the device B, okay, until the message is retrieved. All right. While this is happening, there is a logical communication or logical connection. So the application layer, okay, will communicate with the application layer. So layer to layer communication. And the presentation will connect with the presentation, layer to layer presentation. And the session, they will connect together, session to session communication. Same thing with the transport. Same thing in here, network with the network, data link with the data link, and so on and so forth. So there is two ways of the flow of the data: real data flow and logical data flow. All right, logical data flow. All right, it will be clear later if it's not clear right now. Again, let's go again, repeat what I said. The OSI reference model has how many layers? 7.
7.
Okay, from bottom to up: physical, data link, network, transport, session, presentation, and application. All right, and the data starts from up, down, up, I'm sorry, down, then up, down, then up at the end to the destination. All right. So what will happen? Okay, now the data. So let's say that you have a message. I love Bridgeport. There's a message. All right. It starts from the application. As it goes down, more data will be added to it, and that's what we call it header. So think about the data in here, the D7 in here, the data in the layer 7. Maybe the message is a level Bridgeport. There's a header will be added to it. All right. So the whole thing, the D7 and the H7 will become D6 at the layer 6. And then we're going to add a header 6. Now the whole thing, D6 plus the H6, become D5 as you see it in here, D5. And then we add header 5 to it. All right. And the whole thing, D5 plus H5 becomes D4. And we'll add header 4 to it. And the whole thing, D4 plus H4 becomes D3. And we'll add header 3 to it. And then the D3 plus H3 becomes D2. We add header 2 and trailer 2 to it. At this point on the wire, okay, you'll have zeros and ones, and you'll add header 1 to it. All right, so it becomes 0 and 1s. So the zeros and ones now will be encoded. Encoded, that means the zeros and ones will be converted into
binary.
It's binary. It's a binary into a signal. It will convert it into a signal, as you see it in here. It's gonna go through the transmission medium. All right. So the data hopefully will go as a signal from one side to another side. Hopefully no errors. Hopefully no changes in the data until it comes to the destination. Now at the destination, it will receive the binary data. It will decode it first. It will decode the signal to the binary again. As you see in here, 0, 1, 0, 1, 0, 1. Okay, ends with the 4 0. So seems there is no corrupted data. All right. So what does layer do? What does the layer 1 do? It will receive the data. It reads the H1, okay, and drops it, throw it in the garbage, throw it. Then it moves only, okay, this part up to the layer 2. The layer 2, what does it do? It will take the D2, it will drop the trailer 2, it will drop the header 2, and then moves it up. Now D3, it will drop the header 3 and then moves it up. The layer 4 in here, it will drop the header 4 and moves it up. Layer 5 do the same thing, moves it up. Layer 6 do the same thing, moves it up, until we get to where, to the application layer, it will drop the H7, okay, and moves the data to the destination. So if we started with I love a Bridgeport, we'll end up only with I love a Bridgeport. Okay, so as we go down, the data becomes fatter and fatter and fatter and fatter, and these contain important information. All right, important information, and when it's transmitted, it's gonna go to the other side. It will start reversing the process. It will remove all the headers and trailers as we go up until we receive the package up, right? So that's what is the protocol. That's OSI reference model. And of course, whatever is added in here, it's a thorough process. Maybe we'll talk about it later, what happens. So what is
Professor?
Yes.
So I have a good question. Encoding and decoding is the same of encryption and decryption, or is different?
Different. Okay. Different. So encoding and decoding is converting the data from a binary to a signal. Okay, to electrical signal, or to a light signal. If you are using a fiber, you are sending a light. So how you convert the 0 to a signal and the 1 to a signal, or to a light. All right, that's encoding. Encryption is a completely different story. That's for security, that you garble the data. So you have a data, okay, then you apply algorithm like this, triple this, ES, whatever, the algorithm, and the data will look completely garbled. All right. So you send the data, you encrypt it, it will be received by the destination. The destination will do the decryption. All right.
I see.
So that's for security, and this is for transmission.
Okay.
All right. So the physical layer is responsible for moving individual bits from one node to the next. That's the physical layer, layer 1. It moves the data from one node to the other node. All right. So each one of the layer provide service to the layer above it. So layer 1 provides service to layer 2, 2 to 3, 3 to 4. So they are completely independent. So layer 2 does not care what layer 4 does. It cares about what is beneath it and what's above it. That's it. All right. And that standard allow people to work in this arena without worrying about anything else. So in the physical layer, to transmit bits over medium to provide mechanical and electrical specification. All right. Again, in here, what we did, we converted to electrical signal. All right. This is the job of the physical layer. The layer above it is the data link layer. Okay. The data link layer to organize bits into frames to provide hop-to-hop delivery. Okay, we'll talk about it more later. But layer 2, we call it at this level what we call it. Here we call it binary data. In here what we call it frame. So in the layer 2 we call it frame. All right, we call it frame. So the data at each layer has different meaning. Has different meaning. I'll give you example. All right. What is my name?
Abu Snaid.
Okay. So okay, my name Abu Znaid. So that's my abstract name. What is my name in the class? Professor Abu Znaid.
Professor Abu Snaid, yeah.
Okay. What is my name in my house?
Probably your first name?
No, Dad.
Dad, yeah.
Okay. I wish I'm not called by first name by my children. Dad. Okay. Okay, or father. Right. All right. So the same thing. The data in here and the layer 2 called frame. Okay, frame. All right. In the layer 3 is called packet. Packet. In here called segment. Called segment. So you have really to know these terms. But when somebody tell you that segment, you need to know, oh, this is like layer 4. Frame is layer 2. Okay. So to organize bits into frames and to provide hop by hop delivery. All right. Then let's go to the network layer, which is in here, the layer number 3, the network layer. What's the function? Okay, what are the function is to move packets. So what we call the data at the network layer? Packets. We call it packet. What we call it in the data link? Frame. We call it frame.
Right.
All right. So to move packets from source to destination, from the source to the destination to provide internetworking. All right. So in the data link layer, it only moves the data to the neighbor. They have to be connected together. But in here, it could move the data from a computer in China to a computer in Somalia. There's no problem. Okay, they don't have to be interconnected. Then we move up to where? To the transport layer. It provides reliable process-to-process message delivery and error recovery. So who's responsible in the error recovery? Transport layer. And then here it's a process to process. Okay. Okay. So in the network layer, what kind of address we have? The IP address. The IP address. What is the size of the IP address? 32 bits. 32 bits. All right. In the data link layer, what is the address we use?
MAC address,
The MAC address. What is the size of the MAC address?
48.
48 bits. When we go to the transport layer, okay, you're talking about a process. So the process uses what? Ports.
TCP UDP,
You're
TCP.
sure, but so what is the address for the process?
IP,
It's
IP
the
address.
no, the IP it works in
Hmm.
network layer. Here we have ports. So if the
So
process is HTTP, what port we are using? Okay,
480 or 443?
80. No, HTTP is 80. 443 is HTTPS. So different protocol. There is an S there. If we are using Telnet, which port? 23.
23?
Yes. If we are using SSH, which port?
25.
22. 22. If you are using FTP, it's port 21.
One.
Okay, so don't worry. I mean, these are like well-known ports. If you don't know them, you should know them in near future. All right. So we'll go up to the session. Okay, to establish, manage, and terminate sessions. Usually, for example, in your computer, how many connections you could have? Many. You don't have one session. You have multiple sessions. So, for example, if I try to show you this in here. Okay, so in here I have a session with cnn.com, right? If I open another one, cnn.com, okay, this is another session. If I open another one, okay, cnn.com, so you could have multiple sessions with the same IP address. You agree? So I have session,
Yes.
session, session. All right, I have multiple sessions with multiple IP addresses. So the session is to establish, manage, and terminate sessions.
Does it have a connection with the RAM?
What?
Does it have a connection with the RAM?
With the RAM, you said?
Yeah.
No, I mean, it has nothing to do with the RAM. Remember, in this case, in here, okay, I'm connected with the CNN, so I'm using the same IP address. You agree? Same IP address. I'm using the same port number, which is 88, but there is multiple sessions. So how you handle multiple sessions of communication? All right? You don't want them all in the same trunk. If they go in the same trunk, everything will be mixed. So you'll have multiple sessions, right? Then you have the presentation. The presentation is how to translate, encrypt, and compress data. So data usually compressed, could be encrypted, could be translated from one format to another format, from ASCII to APSIDIC, from different format. So that is for a presentation. Then the application is to allow access to the network resources. Okay, so using www, using like mail server, whatever. Okay, different application layer. So let's review. All right. So how many layers we gonna have? Seven. We started from
7.
from bottom up. Physical. The physical it's a signal. It's just converting the data into signals. Okay, according to certain specifications. So encoding and decoding. Encoding at the sender, decoding at the receiver. All right. So in here we have a signal. In the data link layer, what we call it a frame. We have a frame, and that will allow neighbors to communicate hop to hop. All right. And then, what is the address in the data link? Is the MAC
MAC
address.
address.
And the MAC address size is how long? 48 bits.
48.
48 bits. All right. All right. So when you go up, you have the network layer, which we call it a packet. And here where we have the IP address, we'll have the IP address. All right. And then on top of that, we'll have the process to process delivery, TCP, and there is two main protocols running here, UDP, okay, and TCP, UDP and TCP. We'll talk about them later. Then we have the session to manage, establish, terminate sessions, and then we have the presentation, translate and encrypt and compress the data. All right, and then you have the application which allow access to the whole network. All right, very simple. All right. So each one of the functions of each of the layers are complex and it could be achieved in multiple numerous ways. All right. So they need to be explained. All right. So that's the OSI reference model. This is your Bible. This is something that you have in your mind. This is needed everywhere in your life. It's needed if you do any cloud computing, if you do network security, if you do communications, if you do networking, if you do Cisco certifications, if you do even programming, you have to have it in your mind and you have to understand it very well. It's the OSI reference model. Now, the de facto or the practical one is the TCPIP protocol suite. All right. And it's originally, as I said, started in the army as ARPANET, but it's now is the de facto protocol. All right, TCP is the de facto protocol used. Okay, so how we compare the layers there is like this. So okay, so in the physical layer, layer one will have the hardware devices. All right, the data link, it will map to the network interface. So data link is network interface. The network is something called internet, where they have the IP address. Transport to transport and application to application. So we only have 5 layers. This is the original layers, and this is the layers used in multiple resources. So you have physical, data link, network, transport, application. So where is presentation and session? They are part of the application. They are part of the application. All right. For the TCP/IP reference, they use the internet instead of the network. They use a network interface instead of data link, hardware devices instead of physical devices. You should know this and you should know this because you could read it differently. If you need to look how they relate to each other, so physical. First of all, this is the OSI reference model, and this is the TCP/IP protocol suite. So the physical data link is a data link, network, transport, and these in here is kind of blended together into the application. All right. So the application includes several application protocols, like HTTP is in the application, right? HTTPS in the application, FTP in the application, Telnet is in the application. SSH is in the application. SNMP is in the application. All of these are application layer protocols. You go down to the transport layer, you have UDP and TCPs. Okay, UDP and TCP. UDP is a connection oriented protocol. TCP is a connection-oriented protocol. UDP is a connectionless. So there is two type of protocol, either connection-oriented or connectionless. We'll explain that later. Okay, just remember that it's a connection-oriented and connectionless. All right. Then in the network layer, we have two main protocols there. There are other protocols, but what are the two main protocols you could use? IP version 4 and IP version 6. Okay, IP version 4 and IP version 6. What is the size of IP? What is the size of IP version 4?
32.
32 bits. And what is the size of IP version 6?
128.
128 bits. Okay, we'll cover all of that later, so don't worry too much. Then we have in here the data link blended with the physical, which is underlying LAN and WAN technology, what we have in here. All right, that's how we map things together. So you see in here a private net. So node A, it could be me. Node B could be any of you. All right. So basically, it's like a switched network. So there's no direct connection between node A and B. What will happen that node and link, this is link 1 connected to the router 1. Router 1 connects link 1 with link 2 with link 3. Router 3 connects router 3 with router 4. and so on and so forth. So router 1 also is connected to router 2 via link 2. So when the data is transmitted from node A to node B, it's not necessary that it will flow through the same path. So it could go take this path in here, or it could go the lower path in here, right? So the data could be transferred and reach out to this destination using different path. All right. So communication at the physical layer, as you see in here, node A and node B. In the middle, you have router 1, router 2, router 3. So it goes from the physical layer, link 1, it will go to the router 1. Router 1 will connect it to link 3. Using link 3, it will connect it to the layer 3. And layer 3 will connect the data using link 5 to layer 4. Layer 4 will send the data through link 6 to the physical machine. So as you see in here, the data went from A to router 1 to router 3 to router 4 and until it goes to the destination. It could have taken the upper route. There is no problem with that. So the unit of communication at the physical layer is the bit. So what we are transmitting at the lower level in here, bits, bits. And that's how we measure the speed. Okay, is it like 10 megabits, not bytes, bits, bit. So it's like 10 megabits per second, or is it 100 megabits per second, or it's more or less. Okay, 1 gig, 10 gig, 4 gig, 2 gig bits per second. That's how we measure the data there in the second. So the unit of communication at the physical layer is in bits. All right. So communication at the data link layer, as you see in here. Okay, A again to the physical layer. It's gonna go all the way here. Then gonna go to the network layer. Gonna come back. Okay, until it goes to the destination. Okay, the unit of communication at the data link layer is frame. Remember that we said bits, then the data link we have frame, and I'm sure you remember the upper level, it will be packet, and then it will be segment, right? And all the way top, it will be message, right? So look in here what will happen. So it goes from the network to the data link to the physical, goes all the way up, come back down, and so on and so forth until it goes to the destination. All right, so that's at the network layer. What you notice in here that the communication is end to end, end to end, while here it was hop to hop, the data hop to hop. So the bits will be transferred from here to here, they will be regenerated again, sent here to here, and so on and so forth. However, at the network layer, it's like end-to-end communication. It goes from A computer all the way to the B computer. All right. All right. So, and remember the datagram in here, the datagram. Uh, the unit of communication at the network layer is a datagram. Is the datagram. All right. So, okay. So the unit of communication and the network layer is a datagram. All right. So, and then you have the communication at the transport layer. Okay. So transport, network, data link, physical. All right. You're gonna go up, down, until it goes to that. Okay. So that we'll call it segment. So the data unit in here we call it segment. Okay. At the transport layer we call it segment. All right. So the unit of communication at the transport layer is a segment. Sometimes we call it user datagram, or sometimes we call it a packet. Sometimes we call it a packet, depending on the specific protocol used in this layer. So it could be a datagram, a packet, uh, uh, and you know source packet. So communication at application layer. So the application is gonna go from the application, transport, network, data link. Again, it's end to end. And what we call it at the application, we call it message. We call it message. All right. So let's repeat one more time. Just make sure that we got it all right. Okay. So in here, okay, the communication and the physical layer, the unit is the bits. So you see it bits in here. And then the communication at the data link layer, we call it a frame, and still hop to hop. And then at the network layer, we call it datagram. Okay, datagram. Okay, and then at the transport, we call it segment, we call it sometimes packet, we call it sometimes user datagram. Okay, there's multiple names. And at the application layer, we call it message. We call it message. All right. So the unit for communication at the application layer is a message. It's a message. All right. Then let's take quickly at the addressing. So there's 4 levels of addresses are used in the internet employing the TCP/IP protocol. So there is a physical address, okay, which is the MAC address, and there is the logical address, which is the IP address, and there is the port address. Okay, physical layer. If it's a MAC address, how many bits? 48 bits. And if it's the logical address it's what? The IP address
32.
with 32 or 128. If it's IP6, it will be 128. The port address, what is the size of the port address?
Just 2 numbers, 3.
2 bits.
16 bits. Okay. And there is application specific address, and each application is different, right? So each address is related to one layer in the TCP/IP architecture. So again, if you look at the addressing, in the application is the application address, and then transport we have the port, in the network we have the IP address, in the data link we have the MAC address, the hardware address, the MAC address. Okay. So physical address, logical address, port address, application specific address. Let's quickly take a look at that. So then you have a message and you have a segment. So application layer, we have a message. So there is a application specific address. So for example, if you are using HTTP, what will be the address? A URL, right? Right? Could be a URL or something like that. Okay. If you use, okay, so every application will have different address. Then at the transport layer we have segment, right? Segment or a packet. Sometimes you call it packet, segment or packet, and we have the port address. At the datagram, at the network layer, we have a datagram, and we call it logical address, or it's in the IP address. And in the frame, we'll have the physical address or the MAC address and the data link layer. Okay, and here we have bits. There is no addresses. So it's a very, very, very important to just put these information in your mind, and it makes a difference. So if somebody's talking about the segment, you should know this is that transport layer, or a packet is a transport layer. If somebody's talking about frame, then you know they are talking about the data link layer. So it's a very, very important to somehow make it stay in your mind. This in here. So in here, okay, physical address. So let's take a look at the physical address in here example. So as you see in here, okay, you have a sender. The address is 10. There is in between in here you have 28, 53, 87. So as you look at the data, it will be included in the frame. Okay, in the frame, it will be included the addresses, the physical addresses. So what does it say in here? The source address is 10 and the destination address is 87. So the packet, this packet will be sent. It's gonna come in here. All right. So okay, the physical address of port 2 in here is what? 28. But it says the destination is 87. So definitely it's not going to go up. It moves on to port 3 in here. In port 3, the address, the physical address is 53. However, the packet says the destination address is 87. So it's not going to go to 53. It moves on to here, and then it comes in here. So in here, what does it say? The receiver address is 87, and then here the original packet says the address 87. So this will receive the packet and will take it. The reason for that, the destination address equals to its address. So that means the packet was, or the frame was, directed to this receiver. So you see the importance of the addresses, the physical addresses. The packets, the frames will include source address and destination address. And it's exactly like somebody, okay, let's say that the address is 55 Main Street. All right. So the postman knocks on the first door. Are you 55 Main Street? No. Move on, leave. Then he knock on the next door. Are you 55 Main Street? No. Go to the next door. Okay, until it goes to a room, a house. Knock on the door. Are you 55 Main Street? Yes. Then the destination address on the ladder equal to your address, you'll give it to him. The same thing. That's the same thing he's doing. All right. So where is the 87 and 10? Where is the source address and destination address included? Where is it included?
Header?
In the header. It will be included in the header, right? That's why we have the header. All right. So this is an example for a physical address. It's a 6 byte. 6 byte means 48 bits, 12 hexadecimal digits physical address. So as we will see, most local area network use 48 bit 6 byte physical address written as 12 hexadecimal digits. Every byte 2 hexadecimal. So 2 plus 2 plus 2 plus 2, and that is 1, 2, 3, 4, 5, 6. Yeah, that will be the physical hard disk drive. All right, so let's take a look at the next address in here. So in here, all right, so this is like, okay, the physical address for this is 10, but the logical address is A. All right, and okay, and the data needs to go to the destination B. As you see in here, the the source physical address is 10, the destination is 20. All right, in here the logical address the source is A and the destination B. So remember, in the physical address only it works in the same network. So the physical address does not go across the router. All right. So in here it's gonna go, okay, source 10, destination 20, gonna go to here. Okay, this is source 10, destination 20. All right. Okay, so in here the address in here in this network F and 20. So F and 20. If 20 is the address of the router, and F is the physical address of the router. So this will connect with another router, another network. Okay. Now in the other network, so when you look at the logical address in the packet never changes. So A is the source, P is the destination. A is source, P is the destination. AP, AP until it goes to the P node. So the logical address from source to destination never changes, never changes. However, the physical address changes, okay, because it has to move. I mean, the physical address only could see the neighbor. All right, so this is in here it says a 20, okay, and the destination is 10. Okay, the destination is 10. So it's gonna go here 10, and the destination is 10, which is the address of the nearby router. Then after this interface in here, okay, then after that it's gonna move, okay, the source address in here, the source address in here is 10 and the destination is 20. Gonna come in here, the source address before it moves down is 99 and the destination is 33. So it's gonna go from here to here. Now in here the source address is 99 and the destination is uh, um, 33. Came in here. Now it will change to the source address of this and destination of the next one until it goes to the destination. So the source address will keep changing, uh, at the routers. Okay, source address and destination address will keep changing at the routers. So here, 1020 until it gets to the router. The router will receive it, and the router will change, the source here 99 and the destination in here is 33. All right, and then so in the same link will stay until they hit the router. The router now it will switch, so it will put the source in here, which is like 66, and the destination in here, which is 95, until it gets to the destination. So again, what we are trying to say, the logical address will stay, the IP address will stay with the packet until you are at the end. The physical address will change when you change the physical network. So this is one segment, it will have same physical address, 2010. When it goes to a different physical network, it will change the addresses. When it goes to the next physical network, it will change the addresses. All right, that's why we call the physical address is hop by hop. Is it clear?
Yes.
All right.
Yes.
So the physical address will change from hop to hop, but the logical address remain the same until at the end. So the figure 218 shows where's 218 in here. Shows two computers communicating via the internet. The sending computer is running 3 processes at this time with port addresses A, B, and C. The receiving computer is running 2 processes at this time with port addresses J and K. Process A in the sending computer needs to communicate with the process J in the receiving computer. Note that although both computers are using the same application FTP, for example, the port addresses are different because one is a client program and the other is a server program. As we will see, okay, we'll talk about it later. But anyways, the port numbers as you see in here, so what they are trying to do that you have 3 processes, okay, at the application layer. So this is process A, B, C. All right, so it's gonna go through the sender data. So in here what you will have the source of process and the destination of process. So from here you know that this process will go all the way to communicate with the J process there. All right, so in here again, when you go down, you add to the header the logical address A and capital P. When you go down, so you have the port addresses, you have the logical addresses, and you'll have, okay, as well the physical addresses in the header in here, the physical addresses in here. When it moves, it's gonna go up. When it comes to here, it knows that has to look for the J process and connect. So this is a process to process communication. Process to process communication. All right, and that's what we have in the application layer. So the physical addresses change from hop to hop, but the logical and port addresses usually remain the same until the end. Until the end. So as we will see in the future chapters, a port address is 16-bit address represented by a decimal number. Okay, so 753, okay, 80 for example for HTTP, 443 is for HTTPS, 22 for SSH, 23 for Telnet, 21 for FTP, 25 for Simple Mail Transfer Protocol, so on forth. So that's how is the addresses. All right, is it too much of information today?
Yes.
Yeah.
All right. I'm wondering if there is anybody in the class yet. I see all circles in here. I'm not sure if we have students remaining after all of this heavy class.